In 1881, it was first noticed that in many real-life sets of numerical data, the leading digit is likely to be small. This was noticed by American astronomer Simon Newcomb, who published an article about it, pointing out that in log tables, some pages were out more than others, which was due to more frequent use of those pages. Now, this phenomenon is more commonly known as Bamford's law, or the law of the first digit. To learn more about this law, I offer 2 videos from channels Numberphile and Minding the Data, links in the description. The goal of this video is to understand why does this law work? And our path to understanding lies in the question, is power of 2 more likely to start with this or another leading digit? Let's start by simply writing some amount of powers of 2. For clarity, we color in the same color all those numbers whose leading digit is the same. So, numbers with leading digit 1 are yellow, and numbers with leading digit 2 are orange, and so on. You may have already noticed some patterns. For example, numbers with leading digit 1 are followed by numbers with leading digit 2 and 3. Or numbers with leading digit 4 are followed by numbers with leading digit 8 and less often with 9. But in this video, I do not use this. I want to give a more general picture. Let's leave the first 30 and group the numbers into cells with certain leading digits. And then write down in the cells how many numbers are there. In the cell leading digit 1, there is 9. In the cell leading digit 2, there is 6, and so on. It is clear that the sum of the numbers in the cells is equal to 30, since we have not added or removed anything during the grouping. The probability that the number chosen from those powers of 2 has leading digit 1 is the ratio of the number written in the cell leading digit 1 to the number of all possible cases. Similarly, we calculate probabilities for other outcomes using the same method. Let's illustrate these probabilities on a graph. Here, by default, we have assumed that all these 30 powers of 2 have the same probability of occurrence. In this case, everything is standard. For example, let's turn powers of 2 yellow if the first digit is 1 and blue otherwise. The order and probability of an outcome are not related. However, in the case of infinite number of powers of 2, everything is much more complicated. By reordering, you can completely change the frequency of occurrence of numbers with a leading digit 1, the yellow ones. So the order now matters. The probability of falling yellow is considered the limit of probabilities in the finite cases when the number of elements tends to infinity. As you may have already understood, here, according to the scenario, we need to look at the probabilities on a graph while the number of elements tends to infinity. But I can't resist adding a little beauty. Let's look not only at the case of powers of 2, but also powers with other bases too. And again. Why do probability graphs look the same in all cases, but only differ with the base 10, leaving aside the obvious answer that powers of 10 always begin with 1? What is the fundamental difference between the numbers 10 and 2? We will answer all these questions in this video. Let's look at the sequence of powers of 2 from a different point of view, namely, put them into a number line. Note that then it is not necessary to know the exact value of the number in order to understand which digit this number begins with. It's enough to know only in what interval the number is. For clarity, using colors as indicators of the first digit of the number, we fill in the spaces containing powers of 2 with the corresponding colors. For example, we don't need to know the exact value of 2 to the power of 11 to understand which digit the number starts with. It's enough to know that this number is between the numbers 2000 and 3000 to understand that this number begins with the digit 2. In addition, any other number in this interval also starts with the digit 2. And a number in the range from 4000 to 5000 starts with the digit 4. Another example is the interval from the 500 to 600, where any number from this interval begins with the digit 5. Of course, not any number starting with the digit 5 lies in this interval. For example, a number from the interval from 50 to 60. Roughly speaking, the number of zeros may be different. Necessary and sufficient conditions for a number to start with the digit 5, it is that the number belongs to an interval of the form from 5 multiplied by 10 to the power of q to 6 multiplied by the 10 to the power of the same q. This condition can be easily generalized for an arbitrary number k. Now, the adventure begins. By logarithmizing this expression, we achieve a periodic structure. At the bottom is a number line colored according to the leading digits of their numbers. Above, it is another number line where the value of the logarithm is displayed. At this stage, our task is to color the upper number line, inheriting the colors from the bottom number line, by imaging the logarithm. Strictly speaking, a point on the upper number line has the color that its preimage has. For example, the number 0 on the upper number line has a yellow color, since its preimage is 1, which is colored yellow. The resulting color is periodic. In addition, images of powers of 2 are also periodic. Periodic coloring with a period of 1 make it possible to consider only the fractional part of the logarithm in order to know about the leading digits of the preimages. In this example, the numbers x1 and x2. This approach allows us to write down our condition for the leading digit in this form. Since slightly different numbers can have strongly different fractional parts, it is convenient to glue the ends together and get something like a circle with a length of 1. And now the mapping is continuous. If the points are located with a rational periodicity, then their mapping on a circle of length 1 is looped. since for a certain number, the point has an integer value. And the points on the circle are the vertices of an equilateral polygon. In the case of an irrational period, on the contrary, the points are not looped, since their looping mean that the period multiplied by some natural number is an integer, which cannot be. In the corner, I show the calculation that the logarithm 2 with a base 10 is irrational. From the opposite assumption, it's deduct that some integer power of 2 is equal to some another integer power of 5, which is false. And so the images are not looped. But as in the case of the rational period, they have their own symmetry. This symmetry lies in the equidistribution of those points. Equidistribution means that with a sufficient large number of those points, in our case let's take 200, the length of the arc does not differ much from the ratio of the number of those points that are on the arc to the number of all points, and in the limit these numbers coincide. Unfortunately, I do not prove this statement in this video. It follows from this that the probability of outcome, say with a leading digit 1, is the length of the yellow arc. And so on, we get a Bamford's distribution formula. What do you think? Numerical data, which is leading digit satisfies the Bamford distribution, is always exponential? Write in the comments. For example, in the case of the population of the city, I think it is. Thank you for your watching.